Alright, so today I'm gonna be starting a new playlist, a very important playlist, flow matching, which can be seen as a generalization of diffusion. In diffusion we start with Gaussian. In flow matching, it's more general. There is no stochasticity. You can start from any distribution. And we will talk about optimal transport, which is the straightest flow, and there are rectified flow. There are many different names for flows that are ways to do this flow matching, that is learning this velocity field. And so this iClear paper in 2023 is very important. Also, I should say flow matching is related to many things. It's a continuous version of normalizing flow. We cannot do normalizing flow easily because of that Jacobian each step. We should do that. It is also related to score matching, which I have a playlist for score matching. It is also related to diffusion, which I have a playlist for diffusion on YouTube channel. And there are many other relations to other important topics in machine learning. So we introduce a new paradigm for generative modeling based on continuous normalizing flow. So at the limit, when the discretization becomes smaller, it becomes continuous. But we don't need to do it the way normalizing flow does, because we can learn it. We can learn the velocity field, which is the vector field, allowing us to train continuous normalizing flow at unprecedented scale. Specifically, we present the notion of flow matching. Of course, Maxwell Welling in 2025 wrote a paper variation of flow matching, that they see different variables such as the target Z1, the target variable, different thing as a latent variable. So you also add a term for the KL divergence. And so this flow matching is a simulation-free approach for training continuous normalizing flow. You say it's just a continuous relaxation of prior and the this one is target. So flow matching is compatible with general family of Gaussian probability paths. Oh, by the way, flow matching is also related to this diffusion bridge. Many people argue that even we don't need this stochasticity that they do in diffusion. Also, diffusion, many people argue, is very, very fragile. There is a huge mismatch between training and generation. Some topics like exposure bias have identified this issue. So let's carry on. We find that employing this flow matching with diffusion path results in a more robust and stable. This is what lacks diffusion. It is not robust. It's not stable alternative, because diffusion has many hyperparameters. And when your model has many hyperparameters, it's a really bad thing. Don't think that it's a good thing. It means it's more fragile. It means that if it is not tuned enough, then it cannot even give a good answer. It means that your landscape is like this. Unlike the flow matching, which has a very good gradient, very good landscape, your loss is like this. And an instance of particular interest is using optimal transport. Of course, it's good for mini batches. It's easy to do for mini batches. But there are many other alternatives, like Wasserstein distance, that MMD, maximum mean discrepancy, that I've explained in different videos in machine learning. There are many alternatives to optimal transport. But of course, this one has very beautiful theoretical things, and they talk about different kinds of couplings. For example, optimal transport creates one type of coupling between x0 and x1. So any kind of complex coupling between x0 and x1 is interesting. So the idea is very simple. It's just the ODE, the ODE in ordinary differential equations. So if this is a manifold, over a manifold like a sphere, you can draw some vector field that you can solve differential equations over a manifold. And there are interesting connections to dynamical systems as well. That is not, I haven't seen many articles about that intersection with dynamical system theory, like bifurcation. Nobody talks about the importance of that in flow matching. I don't know why. There are many research ideas that is not even touched. So it's a brand new idea, and in the next 10 years you will see many papers about this flow matching and generalization of flow matching, because even flow matching is generalization of diffusion. So I don't see any reason that we cannot generalize it to more interesting thing that we can analyze it more rigorously. So as I said, this Jacobian normalizing flow is really bothering us. It's not scalable. And people in Microsoft and Google noticed this. So they moved to normalize. They moved to flow matching because they noticed that flow matching is good for 3D protein generation. That they noticed, for example, people in DeepMind noticed that it is not good. Diffusion cannot handle this 3D generation as easy as flow matching. But even flow matching has its own concerns. So this is a continuity equation. If you have studied fluid dynamics as an engineer, you know pretty much about these and how to solve these things. We have different types of PDE: elliptic, hyperbolic, and parabolic. So from appendix of this paper, you can see it's like a change. You think a change of variable, you can easily derive this. And you can write this log of px1. We first solve it using this equation with initial condition in here. So the idea is very simple. You just want to regress the vector field, that is the true vector field. But the true vector field is hard, but the conditional is easy. So the trick is that you condition on that. You condition on x1, your target variable. And it's, it looks like marginalization. If you take this, you're marginalizing, and then doing some base, you will see that it's very simple to derive these things. And then here it's an interesting thing that given the vector field that generates conditional probability, the marginal vector field for U generates a marginal probability in 6. So they can move from marginal probability, the conditional probability, to the actual probability. And now here we propose a simpler objective, which surprisingly will result in the same optima as the original objective. We consider the conditional matching. As I said, we condition on this variable x1. And then this is the equivalent. We consider a conditional probability pass of the form. At any time, there is a mean and a variance. And this is very interesting because you are parameterizing all the probability space. So with this simple thing, with this simple normal distribution, let's see what happens. Oh, it becomes such an interesting thing. So you just consider the flow of this type. Sigma t of x1 of times x and mu t of x1. So there is an infinite number of vector fields that generate any particular probability pass, but the vast majority of these is due to presence of components that leave the underlying distribution invariant. For instance, rotational components where the distribution is rotation invariant, leading to unnecessary extra compute. So we decide to use the simplest vector fill. This simplest one is here, this flow. So according to equation 4, psi of t pushes the noise distribution to probability of x condition on x1. And then just reparameterize this, you get this. Because psi is an invertible affine map, we can use this equation. And here is example of diffusion conditional VF. Here is this optimal transport. In optimal transport, the mu is just tx1 and sigma is just 1 minus. So different combination of mu and sigma leads to different vector fields. Different vector field this leads to different solution of the flow matching. So example 1 was diffusion. You see we use this variance exploding path that is only the variance is time dependent, and here the mean is time dependent, the variance is also time dependent. And here we compare it. In this picture you will see the comparison between optimal transport and the diffusion path. So this conditional flow matching, these laws can be now written like this, because you know the solution, you have parameterized it. And very interesting connection to score matching. Here you will see it's very similar